Not much of announcement after the exam. Hopefully, you guys have a great weekend. I didn't think you got a lot of students watch the video for the lab yet, so probably just working hard a few days from now, I guess. Uh, I'm still grading exams. It's kind of taking a little bit more time than I expected, and I actually learned a lot. Uh, just don't worry about the grading itself. Of course, the multi-choice problem part is going to be the scores that you got from the answers. But for the rest of them part, I'm trying to give you a lot of partial credit if you know how to solve it. At least don't get a correct answer. But I found some, not a lot, but a few or some students actually look up the lecture notes, I guess, or textbook to trying to solve the problem. But once it's kind of obvious, I can just see a lot of gaps in between. There's no way you can just write down the solutions without any steps in between. So uh, if I wrote down some comments on the solution, you guys need to email me to explain what the situation was. And I also have a video, so it should be corresponding to those behavior you have. Uh, I think it's gonna be good start because this is the first exam. Hope you guys have a good big warning here. If it's like exam 2 or final, there's no tolerance at all. All right. Anyway, so like we have the exam 1, quiz 1. Also, I'm trying to minimize the kind of workload for you guys. I know you guys have another labs there. Another courses also have like heavily pouring down all the like homework and assignments like this. And this is actually the really the you got to cover a lot of materials. I'm also hard, but you guys also have some difficulties on that. I totally understand it. So please just focus on the lecture notes and examples and homework problems. And as long as you understand it, I guess you can just nail down all the materials at least we need from this course. All right. All right. Any questions about like exams or labs? Okay. Let's go to lecture. So now we're going to cover some of the example problems of the pipe system, single pipe, multiple pipes, and multiple sub-components within turbine, pump, so on, right? And of course, it's better to better to work on the lab other than the like solving the problems in the textbook. But you're gonna just do both, so you can at least understand how you look up the Moody chart and how you apply the Moody chart to the actual system. So let's just revisit the lab lecture materials that we have done last week. So we have two losses. One is a major losses, another one is a minor losses. So major losses, it's because of the viscosity effects once it flows down the pipe. So we ran the dimensional analysis. Then we found the pi terms, one here, another one here, okay, there again. So this one gives you the pressure drop within the pipe in the dimensionless form. This one gives you the properties of the surface roughness. If it's a laminar flow, we can just ignore it. And there's a Reynolds number, which is going to give you the dimensionless group relating to the velocity in the pipe. And another L over D is going to be the geometry of the pipe, which is simple enough to characterize by the length of the pipe and the diameter of the pipe. Then here, in order to characterize the viscous effects in the pipe, we introduced the friction factor, F. Simply just take the whole part in front of the geometric property because we know we have a linear relationship between the pipe length to the pressure drop. So we can just treat this whole middle into the friction factor. All right, so if it's a head form, the head loss is going to be same as the friction factor multiplied with the L over D, which is geometry of the pipe, and the dynamic pressure, which is came from the dimensionless group of the pressure drop here. If it's a laminar flow, we can just apply the exact solution that we found from the Navier-Stokes equation or the Bernoulli equation. Then turbulent flow, there's two equations. We have Crook-Brook, and another one's a modified Colebrook or Hanlon equation, or you can just use a Moody chart. So if you just finish this course, and I hope you guys at least know this Moody chart was the part of the lecture. You're gonna look up this Moody chart if you deal with any pipe system from now. This one, just single graph gives you the whole bunch of information, a lot relating to the viscous effects in the pipe, and you know how to calculate the pressure drop based on the length of the pipe, diameter of the pipe, material of the media of the flow, and also whether it's the laminar or turbulent. All the information we learn in the chapter, actually partially in chapter 6, 7, and pretty much more than half of the chapter 8, actually described in this Moody chart. What's that? Moody chart? Oh, which one? Oh, oh no, from this course. Yeah. Yeah, you haven't, probably you heard about this chart, but we introduced this one, especially from the lab lecture. I talked about it, and you know how to use it from the example problem from now. So I'm gonna just use it for the example problem. So there's another table we can find in textbook is a surface roughness. Of course, if it's a given in the problem, you can just simply use it. But if it's not, you can just look up this table based on the material, based on the manufacturing method, fabrication, manufacture and fabrication. So there's different types of roughness is characterized within some range. So it's really hard to characterize. Like you can see the range of this, right? It's a 0.003. If it's a smooth enough, it's going to be, there's a 0.10 to the minus 6 to the 7. So if you know this value, now you can plug into the dimensionless group here to find this dimensionless surface roughness divided by the diameter. Then what you can do is you can just look up the number here, then find your curve. If you know the Reynolds number, you can find the location within the graph. If you know the friction factor, you can locate the position there. Or in the opposite way, if you know the friction factor and the Reynolds number, you can characterize the flow based on the surface roughness. So, these equations are the one listed above. The first one is the Colebrook. In this equation, you have a friction factor on the right side and the left side. It's really hard to solve. So you need to either iterate the calculation based on your assumed friction factor, put that into this on the right side and found the left side. And if it's not matched, you can just assume another one going on. So probably like 3 or 4 times of iteration probably give you the right answer. Rough approximate solution. So for the modified one, Hanlon equation gives you the single equation, then friction factor can be found explicitly. So when you just plug the surface roughness and the velocity in the Reynolds number, and if you know what the fluid in the pipe, then you can find the friction factor from this equation. Of course, you can just draw this graph to find the Moody chart. Okay, so it's fine. You can just either use the either equation, but usually you want to just prefer use the second one. The error is going to be like a less than between these two equations, it's going to be less than like 0.5% or less than that. But of course, this is pure empirical data sets, the Moody chart. So even if you can find the right number here, it's going to give you at least like, I don't know what's the rule of thumb in the textbook. I bet it's going to give you at least like 10% error from the Moody chart. But kind of roughly know what the flow within the pipe using this chart. So just do not obsess with the accurate value find in the Moody chart. No, that's not the case. If you find something like, for example, I got the surface roughness, relative surface roughness 0.002 here. Then I want to find the Reynolds number like 10,000. Then you can just follow this graph. Of course, 10,000 is here, there. Then I want to find the friction factor. Then you can locate the points here. It's going to be roughly here. That's a 0.03, 3, 1, 2. No, it's going to the 2. So 32, 34, 36. So it's going to be 0.35. So you can find a number like that. All right. This is rough numbers. So just do not trying to find a really exact number out of this. It's going to give you the 10% error anyway. Okay. So major losses, now we haven't talked about the non-circular pipe, but again, we can use the hydraulic diameter DH instead of a diameter V. So if it's a non-circular pipe, such as like a duct or centric annulus here, then you can just simply replace the D with the hydraulic diameter. If you plug the real cross-section area of the pipe, circular pipe, and the weighted perimeter of the circular pipe, you're going to have the diameter from this equation. So this is a more general form of the diameter, the characteristic length in the Reynolds number. If it's a laminar flow, of course, we have a table. You can just look up the value here to find the C. Of course, assuming you know the Reynolds number. So friction factor is going to be just simply DH or H there. Okay. If it's a duct, you can just plug the numbers here with these numbers. All right, what was the Reynolds number, the friction factor for the Reynolds laminar flow? It was 64 divided by the Reynolds number based on the diameter. So if you look at the values here, the C value is pretty much close to 64 at some point here, right? There's some range close to 64. So it's just a little bit lower or higher than the 64 based on the different shapes of the pipe. So you can just have some sense of the number 64, which is a reference for the circular pipe. And the minor losses. So what do you calculate in the lab? It's going to be minor losses, right? The loss coefficient for each part. Especially you're gonna calculate the friction factor and the surface roughness in the steel pipe and the copper pipe. Then the rest of them is going to be a venturi system. Venturi system also the part of the device measuring the velocity, but also it is a single component within the pipe system. So it has some of the losses. So this is head loss in the various pipe components. So regardless the types or the shape of the components, if it's not the viscous effect, it's all minor losses. Of course, can be more significant than the major losses in some cases. So pressure drop divided by the dynamic pressure is the function of a geometry and the Reynolds number instead of the surface roughness and the length of the pipe, so on. So we just take this whole function as a loss coefficient KL. Then we can just convert it into the head loss form. Then head loss by the minor losses is the KL multiplied by the V squared divided by 2G. All right, it's relatively easier than the major losses. Why? It's basically based on the empirical data set. So if you know the KL, you can just plug that into the equation to find the head loss or the pressure drop by the minor losses. If you go to figure 8.24, 25, 26, 28, so on, you're going to see different types of components and the graph with the Reynolds number versus loss coefficient, or the diameter ratio versus the loss coefficient. So based on the geometry of the duct or the pipe, then you can find the loss coefficient. If it's, for example, like a mitered band was looks like that. The flow is going in and out. If there's no guide vein, you can just use the KL loss coefficient of the 1.1. If there's some guidelines established within the pipe, of course the flows goes more smoothly across the waterway, then you're going to have a lot less loss coefficient 0.2 here. Okay. On the table 8.2, it's going to give you also a lot of loss coefficients. So basically, you know the angles of the bend. Yep, 90 degree, 180, or 45. Well, that's a flange with the flange or threaded. Then based on the flanges, threaded, the connection method, it's going to give it a lot different loss coefficients. For example, a threaded has a lot higher loss coefficient. Of course, you can imagine there's a lot of grooved bumps on the side of the connection, so it occurs a lot of pressure drop because of it. If it's a flange, you can just connect the pipe externally in the outer surface, so it doesn't have any kind of rough surface inside. So you can just use these numbers to find the losses due to each components within the pipe system. I think it's pretty much obvious. So if you look at the valves here, flow valve, angle, gate valve, these two we have in our lab setup. So of course, I didn't ask you to find the loss coefficient of the globe valve and the gate valve. It's not a part of the lab, but you can see the globe valve, if it's a fully open, we still have a 10 loss coefficient. And the gate valve gives you only like 0.15. It's a fully opened, of course. The flow is pretty much at the same flow rate than we designed in the system, but just existence of the globe valve itself gives you the 10 of the loss coefficient. Pretty much a lot of losses, right? Then of course you can find all the different loss coefficient when it opens like a halfway or the quarter, so on. All right. Then now we have a little bit of examples here. I'm not gonna solve all the example problems here. We have a lot of them, and it's going to be very useful when you take the next exam and quizzes. But I'm gonna just post the solutions of these examples. Of course, you have all the numbers and solutions in the textbook, but I'm gonna just solve it again with my words. Then you can just take a look at the steps of the problem solving one by one, line by line, to apply those loss coefficient and find the friction factor for each component. So we can simply use the energy equation. You saw this a lot, right? From the chapters 5. And I just a little bit modified with it. Put the pump head, turbine head. So this is pump. This is turbine. So basically, you can apply the work, put it into the flow itself, or you can extract the energy out of the flow. That's why we place this head on the left side for the pump, and on the right side for the turbine. Then we have a loss head. Okay. Then the rest of the part is going to be just a simply Bernoulli equation. The one thing I want to specify is alpha 1, which is kinematic energy coefficient. But as long as you are dealing with the turbulent flow, we can assume the alpha equals 1. If it's not, yeah, you got to go back to the equation and set the alpha equals 2, which was the part of chapter 5, but you probably really hard to find the laminar flow in these pipe systems, especially with the water. But just bear that in mind. Okay, so this head loss is now we can divide by the major losses and minor losses. Then this is exactly the same equation that we have above. Friction factor and geometry group, non-dimensionless group, then the dynamic pressure term here. Of course, those are in the head form. Another loss coefficient, KL is there, and the V square over 2G is there. And if you have like a longer pipe, you're gonna have more losses from this portion. Then, for example, if you look at the pipe system and it's under sink, you might see a lot of like a 90-degree bend, like more than a 5 or 6, then this part is going to be dominant in the loss. So if you apply this method, you can just solve it, but there's a lot of variables going on. So please just make sure you write down all the variables, especially like density and viscosities are all going to be shown in the table B1, B2, I guess. But also, you can write down all the pressures or velocities or flow rates or the heights or all given in the problem. It's better to just write down on the sides of the paper, then you can just work on the equations. So sometimes you got to use a try and error. You're going to see it in the example problems. Then, of course, when you have all the information in the problem, especially, let's say, for example, you know the pressure drop, you know the velocity and the height differences, so on. Then you need to find the pressure drop. Then, of course, you can just plug the numbers and find the pressure drop. But thing is, if the pressure drop is given, then what if the problem asks you to solve for the diameter or the velocity in the pipe? Then you have to solve it backward. But thing is, you have a V square inside, or the diameter is associated with the especially in the friction factor, you gotta put that into the Reynolds number again. So it's not going to be easy to solve explicitly. So that case, you always just remember just one tip. Assume the friction factor, right? You have a lot of variables, just do this way. Make the assumption that the friction factor is, let's say, 0.002. What you're gonna do is go to Moody chart and use this number. Then if you know the velocity, you can find the radians where. If it's not, you can just make the assumption they have the different variables to find the friction factor. Then you can find the Reynolds number corresponding to the points. Then you can find the velocity. Then, oh, sorry, that's not the one. So here, like 0.2. That's here. Okay, this is 0.002, probably about that area, right? So you can go this way Then find the surface roughness and the Reynolds number. Based on those variables, you can just find the like an location there. Then using these values here, what you're gonna do is find the friction factor again. Then if the friction factor you assume is not corresponding to the one you found in the Moody chart calculation, then you can just reapply the friction factor to the Moody chart and find another Reynolds number and keep doing the iterations like that. So it's better to solve the problem for the try and error method. But just one thing, let's just make the assumption of the value of friction factor. That's going to be the easiest way to solve the problem. All right, if that's the problem in the exam, I'm not gonna ask you to do like more than 2 or 3 iterations. You probably need to just shoot the variables within like a certain range and do like repeat the calculation twice. That will be good enough to make the assumption that your answer is velocity is something number or surface roughness at a certain number, things like that. All right, we have these sets of example problem. If I have more times, I probably have some. I'm gonna solve the first problem. Then I'll just post all the solutions of these examples probably today. All right, then what if we have a multiple pipes components within the system? Of course, some points we have a different diameter within the system. Yeah, that makes sense. That's a usual case. Then what if we have like a different route of the pipes to connect it to the 2 different tanks? If the pipes are connected in series, then you can imagine the total flow rate at the inlet and outlet should be the same, right? So we can just write down the equation that Q1, Q2, Q3 are all the same value. You can just think about this as analogous to the the Ohm's law. We have a little bit different relationship, but they use a lot to this. So V IR. So in this case, we probably have a little bit different. And I don't use that method because it's not corresponding to our system. But usually, if it's laminar flow, it's linearly related to the velocity of the pipe. So we can just use it. But basically, the head loss is going to be just a summation of the head loss within each component. So if I have a head loss here, in other words, like pressure drop for the first segment, second segment, and third segment, then you can just combine all to find the total head loss. What if the pipes are connected in parallels? Then the total flow rate should be Q1, Q2, Q3. So we have to add all together to find the total Q. All right? And head losses is now a little bit different. So head loss should be all the same value for each route. If we have a larger head loss in the first pipe, let's just imagine. That means we have a more resistance in the first pipe, then flow is going to tend to flow down to the second and the third pipes more, then you're gonna have a little bit of change in the velocity and the flow rates in the first pipe, right? So they're gonna find the balance of this resistance. Then the head loss should be all same between the 1, 2, 3 different pipes here. So it's regardless the size of the pipe, regardless the how many components within the pipes, the head loss should be all the same between each pipe segments here. So you're gonna have one more example problem for this. So I'm gonna just trying to solve more these examples with a lot of details inside. Okay, so now pipe flow rate measurement. Let's just derive the equation a little bit here. This is what you're gonna do in the lab too. I introduced a little bit of it in the lab lecture. So from the Bernoulli equation and the continuity, what you have here is here P 2 rho V square. Of course, it's the first one. Then of course you usually have a head loss, but let's say we don't have any losses here. Okay. Just draw something here. Here's a pipe. We have some device here, whether it's a nozzles or orifice or the venturi system, doesn't matter. Let's say we have a little bit of obstacle within the system, then flows accelerated in middle, then expanded again. Okay. And this is the first location, this is the second location. Let's take a look at what's gonna happen between this device. So this is short enough, so we're gonna ignore all the losses, which is the major losses, the minor losses. There's nothing here. That's my assumptions. Then what you're gonna have here is, of course, we are just set it in the horizontal position, so you can just ignore this again. Then the pressure drop, of course, P1 minus P2 is simply 1 over 2 rho V2 square minus V1 square. All right. Then what you're going to do is we introduce the continuity here. So according to the continuity, which is conservation of mass, the flow rate at the inlet should be the same at the outlet too. So Q1 should be same as Q2. Q1, Q2. That means velocity at the inlet multiplied with the cross-sectional area has to be same for the second location, right? Just simply can just rearrange it for the VA. It's going to be AA over V, A2, V2. Okay, what if I just plug this into the Bernoulli equation here? Then it says P1 minus P2 is rho over 2 V2 square minus A1, A2, V2 square. Here. Okay, the cross-sectional area A2 and A1 can be expressed as pi r square, right? Or pi d square over 4. So that means we have a pi can be just eliminated. Then we only have r2 square or 1 square, b2 square. Or it's going to be d2 square and d1 square. That same one. Okay. All right. So if I just rearrange this equation in for the V2, now what it says is, let's just move it first. Let's just skip it. What I'm gonna have is the, let's just change to the D now. And then P1, 2, 2, rho there. Then again, now we have expression that says square root of 2 P1 minus P2 divided by rho. And now we can simplify the form beta Sorry about that. Here, I missed one. Scares here. We have another scares here, and that's going to beta 4 to the 4. Okay, here the beta is simply D2 over D1 or R2 over R1. Okay, now we have an expression of the V2 in terms of the pressure drop and the density and the geometry of the pipe system. Let me more exactly this is here. All right. Okay, so what I'm gonna ask you is, what's the flow rate here? So flow rate has to be ideally the V2 and the A2, right? That's also based on the pressure drop and the cross-sectional area between the point A and the point 2. But this is a single another device within the pipe system. So whenever you put something in the pipe system, it's going to give you, it's not going to give you the 100% efficiency, right? 100% flow rate. No, there's going to be a little bit of the resistance by this device, even if it's a meter. So it's not going to give you the ideal flow rate before and after the venturi system or orifice. Orifice is of course pretty much the obstacle and the nozzle. So what you have is the actual flow rate can be defined by the one more coefficient here. I'm gonna just put C here, and the A2 V2, which is, let me just write down ideal flow rate, and C A2 V2. Then you can just using this equation from the Bernoulli equation, because we make the assumption that there is no losses, right? It's going to be C A2, then square root of a 2 P1 minus P2 rho 1 minus beta 4. So here, this C is what we call discharge coefficient. Of course, for the venturi system, you're going to find this discharge coefficient in the lab. Then this is for, if it's orifice, this discharge coefficient for the orifice, nozzle, and venturi system. So they use a subscript O, N, and V. If you go to textbook, I just posted all the plots here. So this is the empirical data set for the orifice meter. According to this plot, if you know the velocity at the throttle, so of course this is always the velocity at the throttle here. This is 1, this is 2. Then when you have the Reynolds number, which is based on the velocity, then based on the velocity of the flow, you can find the discharge coefficient of the orifice here. If you know the discharge coefficient here, let's go back. Then you can find the actual flow rate. Or if you know the actual flow rate, which is the lab case, in the lab, we measure the Q using the weight tank. Then we know this value. Then you can calculate this value on the right side, which is ideal flow rate. Then you can calculate the discharge coefficient. Then that's what we are calibrating the venturi system. But usually these spec sheet or the calibration table curves are given by the manufacturer. So we can just look up this graph to find what the discharge coefficient by this orifice or nozzles or the venturi system. So that's how you can read this. Of course, for the nozzle system, you might feel the sense of the level of the value here. We have a 0.62, 0.64, 0.6 for the orifice. Of course, we just block it, right? We literally plug the sometimes some types of iris within the pipe. So this is a lot of losses. But for example, like nozzles, we have like a smooth surface of the nozzles, then it's going to increase the velocity, but there's not much of losses in before and after the nozzle system. That's why we have like numbers like more than a 0.95 or 6 here. It's also basically based on the velocity of the flow and the geometry, which is beta, is defined here. Then you can look up what the values of the discharge coefficient for the specific nozzle system. All right, venturi system. We used a lot. We use this venturi system a lot, so you can just go to ASME or just a lot of papers out there. You can just see like probably 80s, not 80s, 60s, 50s. They pretty much set up these equations a lot. So they develop like there's more than 10 equations of the list out there. But usually they suggest to use these equations to find the discharge coefficient of the venturi system. So it's pretty much the curve of the venturi system. You will draw this equation based on the Reynolds number, then compare your discharge coefficient from the lab to the one in the reference data here. Of course, this is also from the empirical data set, so it's not the exact solution, but pretty accurate to anticipate the discharge coefficient in the system. All right, that's pretty much the part of the lab and the part of the chapter 8. What else? Yep. Then you can now have a little bit of time. How much? Let's just copy it. Let's go to this example. Oh, I haven't. All right, let's take a look at one of the example problem here. So we have example problem 8.8. This is the first example problem in the example pipe flow. So we are dealing with the water system. Of course, you can see a lot of complicated system, not that complicated. 90-degree bends here, there, here, there. And we have a globe valves there. There we have a taps here, has a diameter is given. Some loss coefficient is given. The geometry of the diameter is given. Diameter is there. Length is given. Flow rate is given. So it's going to ask you to find the pressure. All right, if you go back to the equation, energy equation especially. All right, here. All right, velocity, which is a part of the flow rate, is given. So you can find this portion is the given term. Height, right? Heights of the system is all given, right? We have a 10 feet there, 10 feet there. That's gonna 20 feet between the first position and the second position. All right, there's no pump. The pressures, yeah, you can find the pressure here. Second is what? The same surroundings. So it means the pressure should be the atmospheric pressure, which is given. Then another velocity here. Of course, it's going to be given. We know that. Height is given. Then there's no turbine. Then there's a head loss. All right. And we can find the P. Just P1 is going to be the one single unknown in the equation. There's no need to, perform the trial and error in this case. So it's gonna we're gonna find the pressure at point 1 if all losses are neglected, and second only for the major losses, and if the all losses included. Of course, I'm gonna just post a solution of these examples too. Let's just do it as much as we can. So if you go to table B.1, you can look up the properties of the water. The density is given. And viscosity, of course. That's why you have the temperature of the water here, just to look up the table. And simply you can just calculate the specific weight, make your life easier. Okay. In the textbook, they use like a 6.4 instead of a 4.7. So just stick to the 1 in textbook, but accurately it's going to be 62.47. So what's given here is the diameter is given 0.75 inches. Of course, you want to convert all in the FPS system, or you can convert everything in the meter system, SI system. That's fine. I'll just divide by 12. You have diameter. The flow rate is given 12 GPM. You can convert it into the feet cubed. All right. Then we have a little bit different size of the faucet there, the 0.5 in diameter. You're gonna just deal with it later. Then let's just apply the equation now. So simply we have a pressure 1, a rho g, alpha 1, that's V1 square, 2g, z1 equals P2, rho alpha 2, V2 square, 2g plus z2. Of course, we have a loss term there. For the first case, we're going to ignore it, all right? If there's no loss. All right, what's given here? Alpha can be assumed to be 1 if it's a turbulent. You're going to check it later. Then if you go back to the problem here, what's the height of the first location here, inlet? We can set it as a datum points, right? If it's datum, we can have a height 1 is a 0 feet. Then here, height 2 is going to be 10 plus 10 is 20. Okay, so this can be 0, this can be 20 feet. What else? The pressure on the right side, the outlet is released to the surroundings. That means we have a pressure of the atmospheric pressure. So P2 is going to be simply atmospheric pressure, PATM, right? What else we have? I think that's good enough to go solve it. If just rearrange it, we just have a P1 equals specific weight Z1 D2 now. Z1 is gone, plus 1 over 2. We have a rows there. B2 square minus B1 square, and plus specific weight, the head loss. Of course, we don't have any head loss. And this is it, right? Then it's time for the velocity. We have a volume flow rate is given. It's simply just velocity multiplied with the cross-sectional area. Then here we have B1 is Q divided by the A. So it's a 0.0267 feet to the q second. It's a pi. That's the diameter is a 0.0625 divided by 2 to the square, right? Then you're gonna have approximately 8.7 feet per second. So you have a velocity now. Then next thing you're gonna do is always find the Reynolds number, right? Whenever you have velocity, you wanna check the Reynolds number to look up the Moody chart or either put it into the equation, but still always you wanna check the Reynolds number. Why? Because you always make the assumptions for the turbulent here to check if the alpha equals to 1. So always do this step, Reynolds number, rho VD over mu. So when you plug the numbers, what do you have? 2.34, 10 to the 5. Do we have this value here? Yeah. Then density 1.94. Then velocity 8.7. Just use like a 3 significant digit at least. 0.0625 diameter. Then what you're gonna have is a 45,000. So is this the turbulent flow? Yes. Larger than the 4,000 turbulent. Then you can just plug all the numbers to find the pressure value here. So P1 is going to be square if there's no loss. So it's purely inertia pressure based on the location and the change in the velocity of the flow. So I'm gonna just post the solution of these examples and others on the canvas. So please take some time to look at it because I don't have enough lecture time to solve all the problems. Of course, if you just ask me during the office hour, I can just help you out, guide to solve the problem. But there's pretty much no time to solve each of the example problems we have here. All right, that's all for today. We're gonna see you again tomorrow. Let me know if you have any questions. I'm gonna just close the recording here.